So hopefully your lunch break was good. And for today, probably, well, let's go through EM first, and then I'll show you how to solve structures, this and that. So we'll continue with this. So as I said, you make sample onto the grid and then freeze them. And to do that, obviously, there's a robot. It's called a VitroBot. So the basic principle is the same thing. You have a tweezer. It's basically everything goes in here. You have a tweezer that holds the grid, the 3 millimeter size grid at the bottom. You apply the sample, and then filter paper come in, blot out the excess liquid, and then the whole thing gets plunged into liquid ethane. Liquid ethane is much higher heat capacity. It freezes much better than liquid nitrogen. So the liquid ethane is cooled by liquid nitrogen, but liquid ethane is the one that's used to freeze the sample, so that essentially you can freeze it without using any cryoprotectant, and then you get vitrified ice, you get glass, you don't get ice. If you get crystalline ice, your sample is destroyed. So you don't want that, so you want vitrified ice. So that's basically the idea. So so this is manufactured by, let me see. Here we go. So here you apply this, so here's the grid, 3 millimeter size. You come in with a pipette, apply about 3.5 microliters solution onto the grid at about 0.5 micromole, 0.2 to 1, depending on your sample for cryo condition. And then filter paper is right here. They come in, the grid is sitting right in the middle. They come in, blot it out, and then everything gets plunged down to be frozen. And this entire chamber is kept at nearly 100% humidity. So it doesn't. That's it. Oh, every page.
Yeah, they are asking every page. Here. So, thanks.
Thank you. Okay, sorry about that. I just signed something away. Don't know what it is. Okay, so as I mentioned earlier, the reason Cryo-EM become very powerful is because of the development of detectors. That enables something called resolution revolution. So revolutionizing the Cryo-EM resolution from 10 angstrom to about 3.5, 4 angstrom, so that you can see individual residues. So near atomic resolution, that's the idea. So, and that's something called the direct electron detectors. They can detect electron directly. Also, it's an instantaneous readout. So used to be with old detectors, you expose the sample for 2 seconds, 6 seconds, whatever it is, you get one image. Now you get movies. So essentially, you get 20 milliseconds, you get a readout, another 20 milliseconds, another readout. The reason for that is when you first shine electrons onto a grid like that, the grid will start moving, buckling, heating up, all that stuff. So over the 6 second, 8 seconds time frame, there's a lot of motion going on that's basically averaged out in the old detector. You don't see that. You lose that, you lost that information because you don't have that time resolution. Now with instantaneous readout, you can see the thing moving around. So you can correct for it, correct for the motion. That's how you can get to higher resolution because of this correction. And that's only possible with this direct electron detector instantaneous readout, essentially. So this 50 frames at 40 milliseconds each, that's 2-second exposure. So that's the critical breakthrough. Okay, used to be over the 2 seconds, you get one image. That said, now you get 50 images in the image stack, all movie essentially. Okay, and then also the detector much better at detecting electrons, much better quantum yield, so giving better quality data as well. So, for example, so typically we have about 23 megapixels on that detector. And each 40-frame movie, this is 50 frame, each 40-frame movie is about 350 megabytes in size, disk space. And then we typically have 3,000 movies, let's say. 3,000 movies will be 1 terabyte already. And nowadays, it's routine to collect 10,000 movies in one day. Used to be 3,000 or 4,000, 5,000 a day. That's a good deal. Now 10,000 is routine. We can get to 15,000 in a day if possible. So we're talking about 3 or 4 terabytes from one day of data collection. So again, the amount of computer technology to process all this data, that's the other thing, the better computers, better data processing software. So all of this technology happened over the last few years, enabling Cryo-EM to be so powerful. But the critical breakthrough is this detector. That's a critical breakthrough. And the theoretical framework, as I mentioned, Jakob Frank already developed all that from his work. So the theoretical work is done, just need a better image quality, and that comes from this capability to model the motion. And then there's something else you'll probably hear about when you read about EM papers, something called the Nyquist frequency. Essentially, EM images are recorded as images at a fixed pixel size. You know what pixel is, right? So there's a fixed pixel size, and that pixel size defines how high a resolution you can achieve. That resolution is twice the pixel size. So for example, this image is acquired at 0.6575 angstrom pixel size. Each pixel is about 0.65 angstroms. That means the maximum resolution you can get from studying such images or structures with this kind of images will be 1.3 angstroms. But that's still much higher than what we'll ever achieve. Okay? So most time this is not limiting, but you'll see soon. And another concept I will mention briefly, I won't explain too much because I don't understand myself that much either, something called the contrast transfer function in Cryo-EM, the electron microscopy. Essentially how the electrons interfere or interfere with each other. So causing these large fluctuations. And to observe that, you take your EM image, you do a Fourier transform. You know about Fourier transform, right? Essentially, you do a Fourier transform EM image, you get this pattern right here. That's the observed contrast transfer function. And now you can fit that to the theoretical function. You get a sense how much information there is on this image. So that's something we can see as well. When we do data processing, we can sort of see how far resolution-wise we can observe our image has the information for. Okay, so I think that's probably, as long as you know there's a contrast transfer function, that's probably good enough. And then final concept is the concept of radiation damage. So as I mentioned, when you shine electrons onto a sample, the sample starts suffering. Same thing, you break bonds, create free radicals, everything else. So you can see essentially when you have a movie that's made of 70 frames here, the first few frames get very high resolution information. It's in beautiful side chain and everything, right? So the envelope is the EM density that you can determine. You can sort of see very beautiful alpha helical structure here, details. In the middle, you can sort of see things start degrading. And then at the end, the last few frames, you can see now the helix become a sausage now. So you saw the resolution picture I showed you earlier. This will be about 5 angstrom already. So you can see the the sample is suffering during this long exposure, 50 electrons or so. So because of that, EM data are collected at low dose to avoid radiation damage. But because of that, we had to average over many, many particles to achieve enough signal. The signal is there, but it's barely visible because of very low dose. But we average many, many particles together to see the particle that I'll show you what that looks like. So nowadays, for single particle Cryo-EM, it's a pretty well-defined flow chart. So you collect data, which is Cryo-EM movies or image stacks. And then you do this motion corrections I mentioned. The particle moves around, but there are ways to track the motion and correct for it. That way, you get a sharper image rather than a blurred average of many, many different states. So that's the trick, okay? And then you also do this counter transfer thing, which I didn't mention here. And then from that corrected image or micrographs, so you have movies. Now, after motion correction, you get a single image. That's called a micrograph. And then in the micrograph, you start looking for particles that belong to your protein or whatever you want to study. And then from these particles, you do 2D classification. I'll explain what that is, to average among particles to find good particles. And then once you have these good particles, then you go, these are still 2D images, not a 3D volume. You have to go from 2D to 3D. So there are ways of doing that as well. I'll briefly explain that. And then once you have 3D volume, you can do, rather than doing 2D classification, you can classify based on volumes, which is much more powerful than classifying in 2 dimensions. And then again, the idea is to find good particles. Once you find good particles, then you can do a 3D refinement to get high resolution structure. So everything happens back and forth here to find the good particles that had a signal for your protein. And then after that, you can do additional things, which I won't have time to talk about. So today, I'll show you roughly this pipeline later as a tutorial, or I'll show you online. Hopefully, I'm still online. So 2D classification. So here's an example of 2D classes, different views of the particle. So many, many different classes. You can see the top ones are better than the bottom ones. These are very blurry. Can you see that? Well, okay, trust me. So essentially, this is a way to tell these are the good particles, these are the not so good, so we focus on the good ones. Use those to go from 2D to 3D. So this requires a little bit of training to sort of recognize good particles, but it's not too bad. I learned how to do it. I mean, I never did EM until 2018. So I've been doing this for 7 years. I've been doing crystallography since 1980s. So give you a perspective. And then how to go from 2D to 3D. And again, this I borrowed from Joachim Frank, but the theoretical framework came from actually 1917, 100 years ago. So the idea is essentially you have real space images, and then you go to you Fourier transform them. And then you can combine the different orientations in Fourier space. And then once you have the Fourier transform, then you can do a back transform to get the structure. Just like crystallography, from one transform you get diffraction pattern. Here you get the Fourier transform. Then you do a back transform, you get the original structure. So that's sort of how it's done. Details, of course, is always a devil, but you don't have to worry about that. So, and then here is an example of 3D classification. So we have 500,000 particles here, 530,000. Actually, I'm not sure you can see that in the back. Can you see this? Oh, you have it in your printout. That's fine. So you have about 500,000 particles, and we classify into 6 different classes. And can you see a difference among them? Yes? Okay. What difference? Different color.
Some of the parts are different, like the bottom part.
Here? Very good. You will be a good structural person. Okay, so if you look at it, okay, as you pointed out, you can sort of see these 2 classes have something here. These 4 classes have nothing here. And this one actually even worse. So this one basically got thrown away. So then these 5 classes are combined together to get the structure here at 3.36 angstrom resolution. Now these 2 classes have something extra here. So they were pulled together, classified again into 6 classes again. You can see this one, again, have nothing here. So that got thrown away again. So the remaining 5 got combined to get the structure at 3.4 angstrom that has something at the bottom here. It turns out this is the one we want. This is actually has the complex with the protein that we want. Actually with RNA as well. So there's a RNA and protein in this little corner right here. As only in a subclass of the particles. Even though these are all good particles, but these only contain basically a subcomplex where these contain the whole thing. And that's what we wanted. So that just shows you the power of 3D classification, that it tells you where you are. Did I explain that okay? All right. If not, there's one more example. Oh, again, this is from Yakum. So ribosome, you know the ratcheting motion, all that stuff. So you can sort of see they could be in different states as well. You could probably classify that as well. So I don't know. Beautiful image from Yakum. Probably he showed that last time. Okay, another example of 3D classification. 700,000 particles from Yakum, actually. So 3D classification, threw away the ones that had very little features. So now 400,000 are left. 3 classifying again. So throw away another 50,000 or so. Now, this is ribosome. So apply a mass for the 60S particle. You get really good looking particles which get to 2.5 angstrom resolution. And this was 2016, 10 years ago. So that was a major achievement to get to about 2.5 angstrom resolution for a ribosome particle. So, and then this is one more example. So starting with 3 million particles. So typically nowadays we start with millions. 3 million, 1 million, 10 million. I mean, it's just how long you like to wait for your computer to finish. But anyway, so starting with 3 million particles, 3D classification, you can see most of these are junk. You have separate blobs. It cannot be the real thing. But this one looks good. 400,000 particles. So that gets selected, classified again. As you can see, junk, not very good. Not very good. The rest got pulled together and then classified. You get the structure at 3.2 angstrom, which contains the central core. And then another particle right here, you can see contains something extra at the periphery. That's about 4.1. And then, so essentially that's how you can zoom in to individual components. So typically what we can do is you can collect a lot of movies and you classify and classify and classify, find different states of your particle if they're there. So it's a very powerful algorithm. So you can, and then you can color your structure based on some resolution. I'll tell you how EM determines resolution. But here for the core, you can see resolution color from 3 angstrom to 4 angstrom being red. So only the periphery is at 4. Everything else is actually 3.5 or better. So it's actually a very good quality structure. And then you can see the periphery is much worse. It's 8 angstrom or worse. Because very flexible, very moving around a lot. By focusing on this region only, you can improve the resolution somewhat. So now it's maybe around 5 angstrom or so. So still not as good as you can get. So we're still trying to figure out how to improve this part of the structure, even though this part actually now is pretty well tied down. But just to give you a sense how you can use 3D classification to get additional information on your structure, on your system. So how does Cryo-EM determine resolution? So in crystallography, you see how far the spots diffract. EM, we don't have that luxury. So we only have images. So what we've done here is, just like you remember this morning, CC1/2, you process that in crystallography, you split that in half, process them separately, and then calculate correlation. Same thing here. You split your particles in half, do 2 separate reconstruction, and then Fourier transform them into Fourier space, and then look at how they correlate to each other. So so-called FSC, Fourier shell correlation. So if the two are identical, correlation will be 1. As they start diverging from each other, correlation gets worse and worse. And there are arguments about exactly where the cutoff should be. You can sort of imagine maybe 1/2 should be the cutoff, maybe a quarter or whatever. And now I think the field has pretty much settled down. This number, 0.143. When the FSC falls below 0.143 is where the resolution is. Why 0.143? Thanks to Richard Henderson, one of the Nobel laureates, together with Yakum. So he developed the theory behind this in 2003. So 10 years before the resolution revolution, 20 years ago now, basically trying to make the resolution definition in EM to be comparable to crystallography based on his thinking and derivation. So this is the final equation that came up. And then if you solve this equation, FSC equals 0.143. So that's where it came from this paper from Richard Henderson back in 2003. So now, I mean, in reality, it doesn't really matter exactly what you use as long as everybody uses the same criteria. So, and this nowadays is so-called gold standard, which is separate reconstruction, Fourier shell correlation, and then when they fall below 0.143 is where the resolution cutoff should be. So in this case, in this structure, it's 2.73 because this is 2.7, this is 3.3, so it's about 2.7 angstrom resolution. So that's how Cryo-EM tells resolution using this as the criteria. So this, forget about that. So in 2020, I published a review about using Cryo-EM for drug discovery. So for that review, I looked in the PDB and see how many Cryo-EM stuff been done over the 10 years before that, and what kind of resolution they achieved. So this was done in the paper was published in 2020. That means the work was done in 2019. I did the analysis in 2019. So as you can see, before 2012, almost all structures are worse than 4 angstrom resolution, blobs, essentially. So starting in 2013, 2014, that's where the new detector was introduced. That's the resolution revolution. Okay? So now you start seeing resolution between 4 and 3.5, which are purple. Green, 3.5 to 3, start showing up as well. And then yellow, 3 to 2.5. And then red, below 2.5. More importantly, you can see before that, there are very few structures by Cryo-EM. And after the new detector, you can see it's exponential growth every year. So that's 2019. If I do it again now, well, the bar probably will be up in the ceiling somewhere. Okay, so those detectors really, really made a tremendous difference. So now, most crystallographers dropped crystallography. They do EM now. My lab is 80% EM, 20% crystallography. We still do some crystallography because one thing I haven't now mentioned is for Cryo-EM these days, there is a molecular size cutoff. If the particle is too small, EM has a hard time to see it. So nowadays, typically it's about 100 kilodalton. So if your sample has a molecular weight less than 100 kilodalton, then it will be more difficult to do by EM using current technology. It's doable. Things that are 60 kilodalton have been done by Cryo-EM. So it's certainly doable, but it's not routine. So for smaller things, crystallography is still the faster way to go. Anyway, so this is 2020 that we published, but that work was done in 2019. And then 2020, 2 papers came out showing that you can achieve 1 angstrom structure by Cryo-EM. So there is no theoretical limitations to how high resolution you can achieve by Cryo-EM. I'll show you 1 angstrom structure for crystallography. Here I show you 1 structure by Cryo-EM. The crystallography structure was done by me. This obviously not done by me, but anyway. You can see now tyrosine at high contours, you can see individual atoms, just like I showed you by crystallography, atomic resolution, because it's 1.25 angstrom resolution. You can see separate resolution. And then at lower contour level, you see a donut now, just like you saw earlier for crystallography. You also see little bumps, which are the hydrogens on the phenol ring. You can see them as well. It's the same thing on the aliphatic portion. Of course, this depends on the sample. And it's not trivial to get a structure at 1.25 angstrom resolution. Remember, Nyquist frequency, you need 0.62 angstrom pixel size to get here. So you have to collect a lot of data, a lot of improvements than everything else. Also, this is apoferritin. I told you about lysozyme that is used to test the quality of X-ray machines. Apoferritin is used to test the quality of EM machines. So this is the lysozymal EM. So very good quality sample, then you can push it to 1.25. For most routine things nowadays, we don't really actually go that far, but 2.5, we can very frequently can reach 2.5 angstrom resolution. So, and then we can see all the detail, most of the detail we need to see. Okay, if you are interested in learning more about Cryo-EM, so there are certainly a lot of interesting, useful websites. You can also Wikipedia. You can learn from that as well. The vendor, most of the instruments are manufactured by Thermo Fisher, so you can go to their website and then look at. There are a lot of actually nice videos there as well. You can watch, and then these are nice online tutorials that can help you get a better understanding. Okay. So, all right, what do you have on your slide? This is the end, right? Or there's more? Would I have more? Do I have more after this? On your, I do. Okay, so let's go through that. So this is the data processing demo now. That I will explain this first, and then I'll show you the demo. Okay. So right now, for Cryo-EM, the most popular software, one's called Liang, one's called CryoSPARC. And CryoSPARC is very user-friendly. Has a GUI, graphical user interface. So that's what we use mostly in my lab. So that's what I'll show you today, CryoSPARC. Okay. And the sample we'll use, the test case. Actually, this is the CryoSPARC tutorial test case. You learn how to use CryoSPARC by doing this data processing. So this was published in 2015. A 2.8 angstrom structure of a proteasome, 20S proteasome. It's alpha 7, beta 7 tetramer, 7-fold symmetry. Okay, so 14 subunits and 350 kilodalton. And that's how it looks like. The 7-fold is vertical symmetry. This is vertical. So this is a sample. Okay, that collected data back in probably 2013, 2014, and this was used as the test case. So first step, you import the movies into CryoSPARC. So for this test case, we are only using 20 movies. They probably have thousands, but we're only going to use 20 because just to show that how the program works. And then this movie is collected 38 frames per movie, remember? And then, so 38 frames, each 200 milliseconds, because this was some time ago. Now we can go down to 50 milliseconds. Back then, this is 200 milliseconds. So total exposure time is about 7 seconds per movie. Okay, so you sort of can see 3 representative movies here. And then motion correction. You can see essentially the particles. So the movie is divided into little regions. You can sort of see the particle moving around in the different regions. And then you can sort of see the trace of the particles moving back and forth. So essentially, the 30 is 38, right? Yeah, 38 frames are combined together. The particles are lined individually, and then they're combined together into a single micrograph. And that is shown right here. So that's after motion correction. And then we do contrast transfer function estimation. So here you can see in black is the power spectrum, the Fourier transform of the micrograph, oscillates back and forth. In red is the theoretical contrast transfer function. And overall, it fits very well down here, and then it goes out of kilter here. So then in blue is the fitting between the two. So when the fitting goes below 0.3 or so, that's why it says, okay, that's where the signal cuts off. And that signal corresponds to about 3.2 angstrom resolution. So this image or micrograph has about 3 angstrom or so resolution information in there. Very good quality, even though most of that, this will be very high resolution, so we don't really bother with that. So 3 angstrom. And I'll skip over this. Well, so So that was 2016. So now there's something new technology called micrograph denoiser. So as I mentioned, micrographs are collected at low dose, so they're very, very noisy. So now with AI, of course, everything's possible. Anything's possible. Not everything's possible. So if you AI, you can get rid of the noise here, and then you can compare the original micrograph and the denoised micrograph. Do you see particles here? You do. Well, not really very well, but now do you see them here? Very well. So this is only for helping you to find where the particles are. Once you find them, you use the raw data, of course. You don't use this. This is only the guide to help you find the particles. Very powerful, very useful, actually. Very useful to see where things are. I guess you probably see that better. So next thing is, as I mentioned, we look for particles. You can do them automatically, or you can do them manually. For this, since this is my first time learning Cryo-EM, so I said, what the heck, I'll learn it manually. So I picked 5 particles from each image. So remember that 20 micrographs? I picked 5 in each, so I basically picked 100 particles. There are many, many particles I did not pick. Well, I only need 5. Based on the tutorial, you only need about 5 each. So you can sort of see there are side views. This is the top view right here. You can sort of see a circle. That will be looking from the top. And then side will be a rectangle. So doing Cryo-EM, one thing you learn soon quickly is sort of figure out which view of your particle you're looking at. You have to sort of, in your mind, have a 3-dimensional image of your particle. You sort of see, okay, I'm looking down the particle or looking from the side. Okay? So it doesn't show up very well on the projector, but hopefully it shows up better on your printout. You can sort of see the side view will be a rectangle, the top view will be a circle. So, and then from that, you can do 2D classification based on those 100 particles that I picked manually. You can see top view right here, side view right here, right? See the difference? So essentially, we only see these 2 views, and these are not as good. This is noise, only 2 particles here. So these are very noisy. This one, 2 particles are very close together, so that's junk as well. But there are very few particles, 2, 3, 4, 6, very few, 11. So most of them, out of the 100, 35 is here, 39 is there. And the reason we pick very few particles, we use these 2 as templates. We'll say, okay, this is how my particles look like. So now I say, go back and look for particles that look like this shape, using these 2 as templates. So something called template picking. So that's shown right here. So template. So now you can see each red dot here represents the particle that's picked by this automatic procedure. So now you picked almost everything. Right? So, and then from there you do 2D classification, you get much better quality 2D classes. And it shows up a little bit. You can sort of see bright lines in the 2Ds here. Do you see them on your printouts? Do you see, I see them here. You see some bright lines here. So that shows you that the quality of the 2D classification is good, very good, because that represents secondary structures in your protein. So if you don't have it, you don't see this much detail. You can sort of see the layers in the structure. 1 layer, another layer, another layer, 4 layers, just like the structure. Alpha 7, beta 7. And then this is the side view, the top view. You can sort of see the 7-fold symmetry, 7 spikes here. So it tells you that you're really on the right track, that you have good quality particles. In this case, 2 views only, side view, top view. So essentially, we take these good particles and throw away the bad ones. Okay? And then from there, we can go from 2D to 3D. So here is generating a 3D shape from the 2D images. You can sort of see if the shape looks right. So 3 different projections. This is Z, this is Y, so this is down axis, down x-axis. This is X and Z, so it's down y-axis. This is X and Y, so it's down z-axis. So you always put the smallest cross-section along Z. So essentially, looking down the axis will be, or the top view will be along Z. So you can see here, 1, 2, 3, 4, 5, 6, 7, 7-fold symmetry also shows up here pretty nicely. So it has the right shape already from those good 2D particles. And then you use those particles to refine the 3D reconstruction. So again, the different views, down X, down Y, down Z. So 1, 2, 3, 4, 5, 6, 7. Sevenfold symmetry. You see the 7 different blue sparks around it. So that gives you the 3D, so-called 3D reconstruction. And then at the end, the resolution, again, using 0.143 as the cutoff, resolution is 2.9. Remember, we used 20 movies here only. It took about 10 minutes or so, half hour, because I was first learning, so it took me a little bit longer. So 20 movies, we can get the structure at 2.9 resolution. Back then, they used thousands. They got 2.5 or something. So if we got to thousands, I think we can easily go to 2.4 or something as well. So that's it. So you have now a 3D volume, 3D EM map that corresponds to your particle. Now you can download it and look at it using your favorite program to look at density, like crystallography program or whatever, to look at the density and then see how it fits your model. Or then you can start fitting a model into your density. So I think, that's it. So as I said, Cryo-EM now, if you have a good sample, you collect good data, you can get it done very quickly. Okay? So that's what I show you in terms of theory of Cryo-EM and also crystallography. So I guess we have another hour or an hour and a half or so, an hour 15 minutes, since we started late. So let me show you some actual cases or go through this again. Okay. Let's see how it works. Oh, let me put the mouse on. Okay, this part, I will just show you how it's done. You don't have to follow exactly. Just watch and see how things happen. So let's do Cryo-EM first. The one I just showed you. The memory is still fresh. So let's show that first. So here is in Pro Movies I showed you. So I mean, what I showed you earlier, actually a screenshot from this. So I guess too small for you in the back, is that right? So this tells you information about the movies. Can you see okay now in the back? Okay. So as I mentioned, 38 images per movie. And then the exposure time is 53 angstroms. And then the pixel size 0.6575. So all that information is put in and loaded 20 movies. Okay? Okay. Well, what's going on? Okay. It's slow, but I think it's working now.
It's working.
Yeah, it's working now. It's just loaded. Yeah. Thank you. Okay, so this is the motion correction I showed you. So essentially it's plotted horizontal axis 38 frames, and then the motion for each frame. Okay, along X, along Y. So it gives you a sense how much particles are moving. And then this is summarized in this plot right here. So most of this is automatic. You don't really have to do anything. Just use the GUI and then start the process. It does everything for you. Really very little control you can have. It's just something you have to go through. And now I'll skip the CTF. Well, maybe not. Let me show you a couple examples. So here is the fitting. So if I zoom in completely, you can sort of see the two different colors, right? Black is the experimental contrast transfunction. Red is the theoretical. You see how well they fit. They oscillate very, very fast. So if it doesn't fit, very clearly you can see the difference. So you can see down here. And then in cyan is the fitting between the two. So you can see very quickly right here, for example, you go out of whack. So this one here, you have red here, but nothing down there. So they're out of whack. So the fitting goes really bad. So this is the green line means the cutoff where the fitting basically no longer meaningful. And that corresponds to 2.7 angstrom. So different image micrographs have different resolution cutoffs, information content. So essentially, but still, generally around 3 angstrom. So here you can see the different particles. They are pretty dense, very close together to each other. But you can see this is a top view, a circlish. And this is the side view, side view, side view. And that the top view is very easy to recognize, basically circles. They're everywhere. And the side views are little rectangles. So you can pick many particles, but I said, okay, 5 per micrograph, 100 total. That's what you needed. So that's what I aimed for. So there are 5 on this one I picked. I just manually go in, clicked on them, and that's it. So and this is the 2D classification. It took 2 minutes to do the calculation from those 100 particles. So very quickly, you get these classes that come out, as I showed you. Let me zoom in a little bit more. So even here now, already, what did I just do? Already you can see the spikes coming out, the 7-fold symmetry of your particle. You can see in the 2D classes already, even though there are very few particles that are used in this. But already it's looking good. They're telling you that essentially that you're on the right track. So this is 35 particles here, and this is 39. You can sort of see 1, 2, 3, 4 layers. Okay? So the next I selected these two classes saying, oh, these are my templates. And then go in and do a template picking right here. So, yeah. So now you can see the program does a much better job. It picks most of the particles that's in this micrograph. Okay? So now we have thousands. So it picked about 20,000 particles, okay, from this process, from 20 micrographs. So roughly about 1,000 per micrograph. That's typically what we have, between 1,000 to 3,000 particles in each micrograph. And then the 2D classification for about 10,000 particles here took about 9 minutes, essentially, to do. So 9 minutes, and now you can see, so now zoom in, you can see better the, do you see the lines here? Okay, so as I mentioned, so that's the indication of secondary structure in your protein. Similar to when you look at the top view, it's not smooth. There are features in it. That basically reflects underlying structural features. Okay? So these are the particles that we use to go. So then from that, we selected particle from that. And then go into 3D volumes. So this is what you saw earlier. So essentially, sevenfold symmetry around the down the particle, and then these are the side views. You can sort of see the different layers of the structure. And then this plot here shows you the orientation of the particle. Okay, so when you look at something, this bottle of water, okay, you can turn 360 this way, right? And that's what you see here, pi to pi, 360. And now you can turn up, down, 180. So 2 pi over 2, pi over 2, 180. So that's basically defines all the pulse orientation of this particle. And then these contours represent how many views you have corresponding to that view, orientation. So as you saw earlier, we only have side views or top views. They're off at 90 degrees, so essentially either side views or top view. Very few things in between. Normally this will be a problem, but this particle, because it has a sevenfold symmetry, so even though you have nothing here, it's not a problem. So, but anyway, so this is the starting point has the volume. And then for this one, we don't need to do 3D classification, so we didn't do that. So from there, straight went into three-dimensional refinement using, let me show you. 8,600 particles, okay? And then you get a 3D volume at 2.94 angstrom resolution. EM is easy, right? So, and then if you look at the plot, the orientation plot I showed you earlier, again, same thing. Top view, side view, nothing in between. But in this case, it's sufficient for us to get a structure that's very good quality. And then here you have a map, refine the density map, and then you can download it. Let's see how long it takes. And this is what you can look at. Oh, pretty slow. All right. So we will now wait for it. I have a copy of it. So So here's the map that I downloaded earlier. So we can open this map. And the program that does that very well is a program called Chimera, which I didn't tell you about, or I think I may have mentioned it, but anyway, if you're interested, you can download and play with it. But for today, I'll just show you how it looks like. So here is a map looking down the down the particle, the 7-fold axis, and then this is the side view. So you can sort of can increase the control level a little bit, get rid of some of the fuzz. Okay. You can see as I spin around, you can see the individual subunits, right? You see that? Each blob is a subunit, and then you have 4 layers, right? So it shows the quality of the EM map. Also, if I zoom in more, right here, you see a helix right here, right? Let me rock a little bit to help you. Do you see that? And then next to it, that's also a helix. So essentially, if you look at it, there are many, many helices in the structure. There's another one over there. You can see the turn right there. And then another one right there. So essentially, it tells you that you are seeing secondary structures, which is not surprising because this is a pretty high resolution structure already. So the EM density actually is very good quality. It can readily fit the model of your protein into this. And as I mentioned, this is a test case. The model is available, so let's get the model. So, and then, okay, let's first look down the 7-fold. You can see essentially very good quality as well. All right, so let's find the model from the PDB, which is right here, this structure right here. So I'll read it in. Okay, so here's the model. It's not a perfect fit because every time you do Cryo-EM, it chooses its own orientation reference point. So it's a little bit different, but we can make them fit, okay? So let me zoom in a little bit. You can see the model has a helix here, right? And that helix should be on here. So we need to turn the model a little bit so that helix goes in here. Okay? So we can do that very easily in Chimera. So we'll turn only the model. Something like this. Reasonably close, and then there is an automatic fitting tool. You can fit the model. Oh, I guess you cannot see this. Let me zoom in a little bit. Can't zoom. So you can basically fit the model into the density. So click on fit. Doesn't fit very well, so let me try it again. Okay. So now, as you can see, the model basically disappeared into the density. You don't see the model anymore. So that means essentially it's a very good fit between the two, and you can also temporarily make the map transparent. Now you can see both. Do you see that? The model, how well let me zoom in a little bit. Okay, so you can see here is the beta sheet, and the model fits very nicely. And then you can see side chains coming out on the beta sheet. And the alpha helix is here, alpha helix here. You can see overall very nice fit. And then side chains in the middle. Yes? Okay. So this is sort of how it works. So you get the EM map like this. And then if you have a model, you can dock it in using Chimera or whatever program your favorite program is. And then after that, you go in manually, change the structure so that it fits the EM density. And then there are refinement programs that can improve the fit between your model and the EM density. So that's doable as well. And then after that's done, then you have your structure done by Cryo-EM. You have a ligand in there. You can find the ligand as well. And then fit the ligand into the density, do the same refinement and everything. So this part is very similar to crystallography. You have a map here. This is the EM map, not electron density. This is actually electrostatic potential. So EM sees electrostatic potential, but the end product here is a contour that shows where your atoms are. So you basically place your atom into the density just like you place the density atom into electron density by crystallography. So that part is essentially identical between crystallography and EM. Okay? So I think this is what I'll show for EM. Is that okay? Do you would like to see other things? Or if not, I'll go back to crystallography, show you a couple of things about crystallography. Okay? So all right, so for this, we'll be using, for crystallography, the workhorse we use is a program called Coot, which I mentioned to you in the write-up. So, and Coot has a very steep learning curve, but it's a very powerful program. So I'll show you a little bit of what you can do in Coot. And then, but first, let me set up the system. So this is lysozyme, as I mentioned earlier. So lysozyme was a test case. So I bought a new X-ray diffraction instrument at Columbia back in 2012, I think. So the vendor came in. They sent us some lysozyme crystals. We collected data at home on that lysozyme crystal. And we used anomalous scattering from sulfur in the lysozyme. So essentially, we determined the location of sulfur atoms in lysozyme and use that to solve the structure. And the electron density map we get is 1.7 angstrom resolution. Okay, so that's the map that you saw. I showed you an example of the map earlier. But now you have to interpret that. I showed you how to interpret manually. Now, of course, you can interpret, now being 10, 20 years ago already, you can interpret automatically using a software. So what I'm going to show you here is the electron density map. Well, not the original map, a better map so that it's easier for you to see. And then the original model that came from the auto interpretation program. So what we do is look at the electron density map, look at the model, and manually adjust the model so that it fit the density better. Okay? All right. So the model is a PDB file, which is right here, lysozyme.pdb. Oh. So lysozyme.pdb is the model, and the map will use this lys01.mtz, which is not the original map, a better quality map, because I guess you never look at electron density that much, so probably a better quality one will be easier for you to see problems. If I show you the wrong map, it might be too not easy for you to see. For me, it's easy because I've been doing this for 40 years now. You have been doing it for 0 years, so I'll try to help you. Okay, so that's what we do. The MTZ just means a file that contains crystallographic information, structure factor intensity, amplitudes, phase information, plus other things. From that, you can calculate electron density map, as I showed you. Okay? So let me show you that. So Coot. How many of you have downloaded Coot actually? You are all done it. Okay. Does it run correctly? Do you have this file? I guess not. So do you have this file? You do. So, okay, let's do it together then. Okay, good. So we'll go through slowly.
Sir, we don't have the file. We have to download it.
I'm sorry.
We don't have the file.
You don't have the file.
Containing lysozyme PDB.
All right. So how can I get it to you? Get the files to you? Will be the best way. I mean, you just need these two files.
You can airdrop the assignment.
Airdrop to whom? To you? And then?
I'll send it on the group.
Okay. That's you? Okay. You got both? Okay, so you're sharing. Okay, I'll give you a few minutes to catch up. That's fine. I'll wait. When you're ready, let me know. Got it? Thank you. You have it now?
Yes, sir.
Great. How are we doing? I don't know, in the back, no response. So are you guys okay? You have the files or? Okay, all right. Okay, so Coot. Start Coot either way you like. Oh, you don't have a mouse, right? Okay. So, yeah, so I brought my mouse all the way from New York, so it's easier, much easier to use a mouse. But anyway, if without a mouse, you can use control. So basically, you need to use the left button, right button, middle wheel, dragging in the middle wheel. So if you know how to do that, you can probably get around. If not, next time, I guess we need to bring a mouse as well, although there's no easy platform to use the mouse on. Anyway, okay. So does yours look like something like this? Similar? So okay. All right. To open a PDF file, you can go File Open, or you can just click on this little folder thing. Okay? And then find the file, which is lesser than the file you just got, lesser than the PDB. Okay? All right. And then say open. So now you have the structure. Oh, let me turn on the symmetry. See something similar? Different? Huh? Same. You can drag around, listen to that. So you can sort of see then you have the protein built in and those little red crosses. These are waters. So the program automatically interprets the electron density. Whatever it can interpret, it builds protein. It cannot interpret, it builds waters. You think there's something there, but doesn't know what it is, so it put a water there. So there's a lot of water. As you move things around, you can see a lot of waters in there. Okay? And then the color scheme right now, well, we can change the color. So let's change the color. Red is oxygen, blue is nitrogen, carbon right now is yellow, which means you cannot tell the difference between carbon and sulfur because sulfur is yellow as well. So let's make the carbon a different color. To do that, under Edit, there's a bond colors. The top is alphabetical. Each menu is alphabetical. So first on bond colors. So click on that. And then drag to the left a little bit so you have room, it doesn't disappear. And then you can just drag this bar around, you can see the color change. Okay? You do the same yourself. Don't watch me. Anyway, so when you're happy with what you have, then change to 0. Which means then carbon will be orange, and then oxygen red, nitrogen blue. Now you can see the sulfurs, which are yellow. So they are the sulfide bonds here in lysozyme. Okay? Do you sort of see similar things? Okay? So, good. Once you're happy with that, just say okay and close the window. Okay. So next thing we need to do, so now we have the model now. Next thing we need to do is, no, you have a question? Or okay? Okay. Oh, maybe it's in the back there are questions. Okay. So next thing we need to do is open the electron density map. So for that, you go to File, Auto Open MTZ, the second option. Because we have an MTZ file, that's the phase information. So open that, click on that, and open the file you just got, which is lot01.mptz, right? That's what I shared with you, I hope. Good. So that's the file you open. Click on that. And now you have electron density. You should see that as a little cage in here. And again, the color is not very beautiful. Let's change the color. To change the color, there is this. Do you have this toolbar? There's a display manager toolbar right here. Do you see that? Do you have it on yours? So click on that. If you don't have that, you can go into Edit, Map Color. You can do that too. Okay? But this toolbar is useful in the sense that you can change the properties. Click on Property, click on Color, and then you can change to any color you want. So I'll make it a cyan. If you like a different color, choose a different color. Do you see what I did? Okay, so on the Display Manager, the first map, click on Properties, then open this dialog, and then scroll down a little bit, you see Color. Click on Color. Now you can, there's a wheel here, you can drag it around to whatever color you like, and, and then you can click on whatever brightness you like. Almost there? Yeah?
Previous step. From the previous step.
Please repeat it.
Pardon.
Previous what?
The previous step.
Previous.
From the color density change. From the color change, how you go?
Oh, how to get here? Oh, I see. Sorry. Okay. So, do you have this? Do you have this? Click on that. And now you see this. No? You do see that. And then click on this. Got it? And now you see this. Now scroll down, you see that. I know, I said Coot has a steep learning curve. Unfortunately, that's.
But we have seen larger density.
Oh, okay, good. So that's under Edit, Map Parameters. Right here. Click on that. So you probably have 30 or something. I have 7. I usually show a smaller area so you don't get distracted. Yeah, so that probably everybody should do that because you have 15. Okay. So I usually use 7. So use a smaller area. You can sort of see, focus more. So if you are seeing a larger thing than mine, you can just go, you can change that as well. So that's under Edit Map Parameters.
So how we have to choose this parameter for the basic space? 7 or 16?
I'm sorry?
How can we how we have to choose this? We have to choose take 7 or 16. So this number, on what basis we have to choose this?
For system?
Like this map parameters. How we have to choose this? What is the basis for it?
Was two what?
What is the basis for this map parameters?
Oh, the basis?
Yeah. How we choose like different numbers? Like you have taken 7 as.
Oh, different. Do you mean the size of the map? You mean? Oh, that's arbitrary. So I usually choose small so you don't get distracted things on the outside. If you want to see more, you can choose a larger radius. And also the larger the radius, the slower it gets, right? The computer has to calculate on the fly. So if you have a very large radius, you have to do a lot of calculations. It slows down the display. So typically I use 7 angstrom. You can go higher, 10 or something if you like, yeah. Okay? All right. Okay, so now we have to go, unfortunately, step through one residue at a time. So to go to a specific residue, there's a little arrow right here. Click on that little arrow. And then always drag to the left so the window stays in the front. So here you can select whatever way you want to display. You can choose this button right here. Then you can select any residue you want to center on. You click on any residue. Let's click on the first one because that's where we want to start building. And then say apply. You can see the display changes. It changes the center of the display. So this is where the center of the display is. You see something similar? You can go anywhere, or you can type in a residue number here if you like. Let's say if you want to go to 20, just put in 20 here, apply. That works too. Okay? Or you want another way? No. You're okay? There's a video too. Okay? So this is where you have to zoom in now. Can you zoom in on yours without the mouse? Can you zoom in? So if you can't, basically right mouse and drag. That's how you zoom in. So now you can see clearly the model better. You can sort of see now, this is N C alpha CO, and then this is the side chain. It's a valine. Do you see that on yours? Okay. No? You cannot zoom in, right? Yeah, you have to zoom in. Yeah, unfortunately, yeah. Anyway, so for this part, maybe follow, I'll explain what I'm doing, and then you can practice with the mouse later after class. So essentially, right drag, zoom in. Now you can see things. Okay? So, since we have a valine here, maybe let me first explain the concept of rotamers to you. I mentioned earlier today, rotamer prefers sidechain conformation, right? Okay, so for that, yeah, maybe just follow me for now so that I can sort of show you what's happening. So I'm temporarily hiding the electron density. So here is the valine residue. So you can see N C alpha CO, and here's the side chain, right? So now, in this conformation, you can see the side chain methyl groups on valine are trans to the main chain, right? So less stereo hindrance. So that's actually a preferred rotamer. So let me show you. This you can probably follow along. So we can change the side chain. So by changing eddy chi angle right here, you can change the side chain. So let me change the side chain around. You can sort of see the difference. So in this view, what do you think? The two methyls are directly above the A and the C. Do you think that's good? That's not good. Stereo hindrance, right? That's cis. So that's not good. So that's an unfavorable side chain conformation. Or you can have something like this. So bifurcating this N-C alpha bond, that will be okay, right? By the same token, if you can have something like that, bifurcating the C alpha C bond, and that will be okay as well. So essentially you can sort of see for valine, maybe there are three conformers. One will be like this, one will be like this, the other one will be like this. And that's exactly what you see. So let me cut out of this. So now you can sort of say, rotamers. So there's a command called rotamers on the side. Okay? You click on rotamers, click on the residue. So first it tells you valine has 3 rotamers. So, and then percentage-wise, 73% look like this, preferred. And then 2 and 3, 20%, 60%. What are those? Click on them, see what it looks like. So number 2, you can see bifurcates this bond, like this, as I showed you earlier. And then number 3 will be the other one. So this is the concept of rotamers, preferred orientation of side chains. So you all know about Ramachandran plot, right? That's preferred configuration of the main chain. This is rotamers are preferred configuration of side chains, again, to minimize stereo hindrance. Valine is a simple one. I can show you something more complicated. And then you see that actually, for example, lysine, arginine, they have so many free bonds, rotatable bonds. You have many, many rotamers, 10, 20, 30 rotamers. But valine is very easy. Typically, you see these 3 possibilities. If you see something that's directly cis, chances are that model needs to be adjusted. That will be unfavorable because of stereo hindrance. Okay? All right. So is that okay? So let me cancel all of this. So I mentioned Coot has a very steep learning curve, but don't be afraid of it because everything's done on the computer. Nothing explodes, nothing crashes. Well, even if your computer crashes, you can restart it. So if something happened, something just kill the program, start it again, start from the beginning again. It's just a matter of practice, play around with it. And you have questions, I guess in the next few days, we'll go through Coot a couple more times to get you more familiar with it. And maybe even for PyMOL, I think it's good to have a mouse. So bring a mouse with you so that you can sort of, even for PyMOL, mouse, the window wheel in PyMOL actually is quite useful as well. So I think it'd be good to have a 3-button or 2-button plus the middle wheel, the mouse, okay? All right, so let me show you a little bit about how to build models, okay? So let's turn the electron density back on. And so you see here the valine. And then before valine, you have continuous density for it, right? So that suggests that there must be another residue before the valine. The program did not know what to do with it, actually build waters into the density. Should not be water, should be basically another residue. You can see this is the main chain, the side chain actually is quite long. And then if you know your amino acids very long linear side chain, what would that be? Which one? Arginine? Lysine? Alanine? Huh? Isoleucine. But isoleucine is branched, right? So long linear side chain. Lysine. Which one? What's wrong with being charged? It's certainly fine. It's on the surface. It's certainly okay to be charged. Or lysine or methionine are the same shape. But methionine will have a sulfur. You have a stronger density for sulfur. But we know that this is lysozyme. We know the sequence should be a lysine. The density actually consists of lysine. So then how do you build it in? So here you said on the menu bar you have add terminal residue. So you can add a residue to the structure. So click on add terminal residue. Click on the valine, anywhere on any atom on the valine. And it builds the residue for you. You can see right here. So a new residue shows up and it builds the alanine because it doesn't know what the sequence is. It always builds alanine first. And then you can modify it later. So you build the alanine there. And then we can go to alanine by doing shift spacebar. It goes to the previous residue right here. Now, if I rotate around a little bit, you can see essentially here's the side chain, here's the main chain. Okay? So now we know it's not alanine, it's a lysine. That's okay. So that's something we can do simple mutate. Okay? So we can mutate any residue you want to whatever else you want. So click on simple mutate. And click on anywhere on the argent alanine, and then a dialog appears, all 20 amino acids alphabetically. So you can basically select whatever you want. In this case, we know it's lysines right here. So select lysine. Okay, kill a mosquito, that's good. All right, so here we have the lysine here, but it doesn't follow the density. It's out of the density completely, right? So we need to fit into the density. So there is something called real space refinement right here, a zone. You can refine a zone of residues into the electron density. So that's what this command does. So you click on that, and it's a zone. Zone means a zone of two residues, but it could be the same residue. That means you need to click on the same residue twice. Okay? So click on the lysine twice, anywhere on the lysine, and you can see everything blew up. You can see basically it gives you a dialog. I mean, bonds are bad, angles are bad, red, and you know red is bad, right? You heard that this morning. So this is all bad. That means it doesn't like it. Why is that? That's because, as I said, the program actually built waters into the density. So now the program is trying to keep the lysine away from these waters. So he knows that water's here. So he knows that lysine cannot be there because they'll be clashing. But we know lysine is correct, water is wrong, so we need to delete the waters. So to do that, so we don't like this. Well, if you don't like it, just say cancel. So reject in this case. And then we just go in and delete the waters. So you can see there are 4 waters. One here, one here, one here, one here. That need to be deleted. So to delete waters, there's a command called delete. Okay? I guess everything, so go to delete. We can go through this again tomorrow if you like, when you have the mouse back and everything. Today, let me show you a little bit, and then tomorrow we'll go through again to get you more familiar with. That's fine too. So it's negotiable. So delete. And again, you can delete almost anything. A residue, a water, other things. In this case, we want to delete a water. So say water. And then at the bottom, it says keep delete active. That's helpful in this case because we want to delete 4 waters. If you don't say this, every time you click delete 1, this window disappears. You have to go back again. So we keep it active so that we can click 4 times and then close the window. That's what this thing does. So we'll leave it on. If you only delete 1 residue, now you don't need to do that. Just click on that, that window disappears automatically. Okay, so we'll keep it active. All right, and then come back here. You can see the cursor change to a cross now. So it tells you that you can select. So click somewhere, and then just click on the waters. 1, 2, 3, 4. So they're all gone now. There's no water in the density anymore. Okay? And when you're done, make sure you close this, because otherwise this is still active. Anything you touch could be deleted. So you want to close this so that delete is no longer active. Okay, so now we can do a real space refine again. So at least it didn't blow up. But this is so far out of the density, it doesn't have a chance to get in here. Well, this is where Coot actually is quite useful. you have a rubber band on this atom. You can drag it. Let me show you. Okay? You can go to the atom, click on it, and drag. Isn't that magical? So we should do this tomorrow, just so that you can drag things around. So now you can see it's okay. But then you can sort of see this angle is horrible. Nitrogen should be up here. There's a big blob right here for the nitrogen. You can see. See right here? A big bump of the nitrogen should be sitting here. So we can drag from here to there. Okay? That's the goal. So go there, click on the nitrogen, and drag. There you go. So it's there. And you can see now it's actually a very good fit to the density, right? And more importantly, now you can see the dialog box, everything's green now. So now we have built in one residue. Does this sort of make sense? How many have lost? I probably lost most of you, right? It's fine. Don't worry. This is the first time you learn Coot. I got lost myself. So you saw how I do it, and try to practice a little bit at home. Oh, not at home. Sorry, you're not going home tonight. Anyway, where you are, that's your homework assignment. Practice a little bit tonight, and tomorrow afternoon during tutorial. Tomorrow I think I'm not doing the tutorial, but anyway, when I come back to do tutorial, first we'll build that last thing again. Okay? So anyway, so this is how you can build in a model into the density. And then if you're happy, you say accept. If you don't happy, say reject. So nothing terminal about it. Until you say accept, nothing happens. Say accept, and now you have the model in the density. Okay? And then the next one, by placing, so the space bar gets you to the next residue. You don't have to go back to this dialog all the time. The space bar goes there. Okay? And then another thing you see here is under validate, there's a command called Ramachandran plot. Okay? So validate Ramachandran plot. And it shows you the Ramachandran plot for your structure. Okay? So in this case, it tells you there are 0 outliers. The quality actually is quite good. And this actually, okay, a few things. So you have circles. Do you have it on your screen? Okay, you see circles. You also see triangles. So circles are any residue. Triangles are glycine, because glycine is special. Why glycine is special? Because it has no side chain. So Ramachandran plot is the main chain stereo hindrance issue. Glycine has no side chain, so it has more freedom compared to other. And then up here, you see a little square, right? So that's a proline. Proline is special too because proline has a cyclic ring in the main chain. So a proline, this phi angle has to be around -60 because the way the bond is structured. So prolines are always somewhere around here. So and then this contour plot is the energy landscape of the main chain conformation. So darker color means lower energy, more favored. Lighter color means higher energy. No color, no contour means very high energy, disfavored. So outlier, essentially. Okay? And this is for all residues. And then if you put your mouse on the triangle, you can see that everything changes. So that's for glycine. Because glycine has no side chain, so it has more allowed regions. So it's a live plot in that way. And if you put your thing on the triangle, on the square, you can see that's for proline. -60 or so, only for proline. Okay? And then finally, this is a live plot. The residue in here are linked to the residue in here. So if you go to any of these dots here, for example, if you go to this dot here, it tells you that's residue 77 asparagine, right? So if you click on it, it centers there. Okay, so if I zoom in, you can see 77 asparagine. So you can go back and forth. This is very useful. If you have an outlier here, you can just click on the outlier, you go right into the electron density and see what's wrong with it. You can fix it. So it tells you exactly where you are. And then that residue will be highlighted green. You can see it's green on the Raman-Chandran plot. That's the center. So now if I go back here and press the space bar, it'll go to residue 78. And then it's over here. So it goes back and forth. You can watch where the residue is in the Raman-Chandran plot by looking for the one that's green. That's your residue. Okay? So you know where you are. Okay, so I guess one more thing we can show. You can draw the amino acid sequence of your protein under draw sequence view, and then you choose the model you want to show. In this case, we only have one, so we can just choose that. And then it comes up with a sequence of your protein in here. And again, that's live too. So you can click anywhere on that sequence. Now you go there. So that's another way of centering anywhere on your protein. If you know where you are, which residue you want to go to, you can just show the sequence. In this case, I click on cysteine 30. Oh, sorry, cysteine 30. And it goes to cysteine 30. So it's a very flexible program, many different ways of doing the same thing. It's your preference, which way you like to go. Okay, this is probably useful, so you sort of know where you are, and then you can click on which residue you want to go to. Okay? So, what else should I show you? Okay, let's go, since we have this up, let's go to residue 5. Click on residue 5. Okay, that's an arginine. So you can see it fit the density very well generally, right? Very good fitting. You can see that the density is zigzagged, the side chain is zigzagging as well. Pretty good fit. But then if you look at the very end of it, if it's centered on the guanidinium group of the lysine, the arginine, you can see, is that a good fit? Yes? Okay. You think so? No? Oh, nothing has no. I'm sorry. I need to come here more often. Yeah, okay. Obviously not good because you can see this goes this way, but the model goes this way. So essentially this needs to be down here, and this needs to be up there, right? So what do? Well, okay, let's try rotamers, okay? Just humor ourselves. Okay, rotamers, arginine. And how many do we have? Let me scroll down. 33. So you have to be lucky to click. I mean, if you had the patience, you click one at a time to figure out which one is the rotamer that corresponds to what you need. But I don't have that kind of patience, so too many rotamers. So let's do real space refinement.
third number. Below that, real space.
I'm sorry?
Below that, real space.
It's below the,
Acting in my dimensional control.
I'm sorry. It's,
You're saying that we have to do real space defining.
uh-huh.
And do the third. That is in control panel.
Don't know what happened here. Oh, here we go. Okay. Anyway, so we have it going. So now I can drag again. Since you like dragging, I'll show you dragging again. So I can start by dragging this atom down here. Let's see what happens.
Showing green right now.
I'm sorry?
It is
All the
showing green.
parameters are green.
All is showing green.
What do you mean?
All parameters are green. This all parameters
Uh-huh.
green in color.
Yeah. That just means the model geometry is good. Has nothing to do with the fitting. Oh, I see. So you're saying these are all green. Yeah, that means the model looks good, but it doesn't fit the density. So that it doesn't care about in this region. It only cares about the model geometry looks good. So you can clearly see it still doesn't fit the density, so I'm going to try to drag this down, and then see what happens. So go there, and then drag. Okay, doesn't do the job. Okay, we'll drag, see now this one is out of density, we'll drag it over. How about this? Looks better? And that's still, everything's still green. Okay, but now you can see clearly it fit the density better here. Okay, so we're happy. So now we say accept. So now we have it here. But that's actually, okay. Let me do space bars, go to the next residue. You can see here, disulfide bond between two cysteines, cysteine and cysteine here, two sulfur, disulfide bond. Very good density for that as well. Okay, so that's not the main region I'll show you here. So let me go here, minimize all the windows. And so let me turn out the map here. So if you look here, you can see we have a helix, right? The chain going this way. Okay, so in Coot, you can measure distances between atoms. So to do that, so under measure, distance and angles, you can measure distance and angles. And then again, a little window shows up. Click on distance, so you're measuring distance. Go back to this window, click somewhere. You're back in the graph window, graphic, and then you just click on the two atoms you want to measure. So now you have basically carbonyl here, 100 bound to amide. The distance is 2.8 angstroms. Okay. And then you can go back, again, activate distance, make another one. And then you can make more if you like. Okay, so one thing you need to remember is these are different windows. So when you're in this window, you're now in that window. When you come back here, you have to click somewhere so that you're back in this window. When you come back here, you click on this window somewhere, or maybe click on this twice. Because you click once, you're only activating this window. And you click again, you select it, come back here, click somewhere else, and then click on the two atoms you want to show the distance of. Okay? So I can draw one more, and then you sort of see a pattern here. Okay, so now you have too many labels on your structure now, right? So you don't like that. Well, I don't like it either. So you can get rid of them by same window right here, clear all atom labels. Click on that. So they're all gone. So now you can see essentially the hydrogen bonding pattern in the helix going around. The carbonyl down below, hydrogen bonding to the ancient amide above it, about 3 angstrom distance, a typical hydrogen bonding distance. Okay? You can also measure angles if you like. As you see right there, you can measure either bond distance or bond angle, but most time I use it for measuring bond length, essentially, how long the distance is between two atoms. Okay? So I think this is sort of a beginner's guide to Coot. And as I said, practice a little bit more. And then next time when I come back to do a tutorial, we'll start with this again so that we're all on the same page, sort of. Okay? So, all right. What else do we want to do? Let's see. Questions? Any questions, I guess, I should say.
Questions?
Nope. So we have another, 10 minutes or something? Okay. Well,
If you want to ask questions right now, it's fine. Otherwise, tomorrow you can pen down whatever queries. And if you want to learn it again a little bit, because today mouse restriction, I think, because of mouse, now you understand the power of mouse. Otherwise, they don't.
yeah, I think a mouse will be helpful. I can go through a couple more residues to show you how to build something.
You can
So
do
then,
also that in
yeah, you can
class,
watch.
you can have the mouse availability.
So let's just go back to the beginning. Turn the map back on. So this is what we built in. The first lysine. And then next one, the valine. Looks reasonable. So we're not going to touch it. Next one, phenylalanine. Looks very good. And this is the glycine. And then arginine we just did. That's fine. Cysteine looks good. Glutamate, you can see it looks very good. That's even water next to the carboxylate. That's good. And then this is the leucine. Very nice. You can see the tetrahedrocarbon right here. You can see this, the bend in the electron density. Very good. And then this is the alanine, a bump of the side chain. That's good. Another alanine. That's good. Another alanine. That's good. And now we have the fun part. Okay, so here we have a methionine based on the sequence, but it's not sitting in the side chain. The density should be right here. But then, no, that, okay. And then, where the side chain is sitting, actually, there's a tryptophan sitting in the density. So the auto interpretation program built the structure wrong in this case. So you think the tryptophan side chain should sit here and has no place for the methionine side chain. So tryptophan had to leave, or to get rid of the tryptophan. So, but where does it go? Well, we go there, we middle click on the tryptophan C beta. You see over here, beautiful density for tryptophan, right? But there's a tyrosine sitting in there. So the program made two mistakes. Essentially, the tyrosine sitting in the tryptophan density, tryptophan got kicked out, and tryptophan sits in the methionine side chain density, and methionine got kicked out. So then let's look at this tyrosine. Where should that go? So middle click again. You can see middle click again. Beautiful density for the tyrosine side chain. So tyrosine should go in here, but then program build 3 waters in there. So same thing, we need to get rid of these 3 waters, and the tyrosine can go in there. The same process. So I can just delete them. And then rotamers. So tyrosine has 4 rotamers. So this is the most preferred at 43%, but the second one is 34%. So let's click on that, see what it looks like. So that's pretty good already. So not the exact fit, but close enough. And the rest we can just do real space refine. And then brings it in. Right? So happy with that. So now we have built in the tryptophan. So now we have to go back, the tyrosine. Now we have to go back find the tryptophan, which is right here. It has the water in there too, so we need to get rid of the water. So okay, so now the side chain is here. So there is something else you can do, something called auto-fit rotamer. Let's try that. So auto-fit rotamer, go here, click on the side chain, and you went in as well. It's fitted pretty nicely as well. So you can have more control. If you don't like this, you can go back, build it again, but in this case, it worked pretty well. So now we just need to go find that methionine, which is right here. You can go click spacebar, you go back to methionine. So we can do auto-fit rotamer again, see what happens. Pretty good. So this is an easy case. That's why I show you to beginners so that you can sort of see what's happening. The quality of the electron density is very good. This is 1.7 angstrom X-ray diffraction map. You can see the side chain zigzagging for this elongated side chain. And then this sulfur has a little bit bigger density because sulfur has more electrons. So all of these information are in the, once you know what you're looking for, you can find them. And they're all here because it's such a high resolution structure. You can see all the details here. So it makes model building very easy, actually also very gratifying. You see your model fit the electron density very nicely. To me, actually, that's really gratifying to see that. So you're really making good progress, and your data actually agree with what you think your protein is. So that's sort of a flavor of what we do. And you may, I mean, lysozyme is 150 residues, so not difficult to do. Now with Cryo-EM, we oftentimes have 1,000 residues. No choice, you have to go through one by one. So my students and postdocs will build the model, and once they're happy with it, they send it to me, and I have to look at them, all of them, one by one. And now I'll tell them, okay, this is wrong, that's wrong, that's wrong. They have to go fix it. So it is a lot of work, but also at the same time, very satisfying to see the model, how well the model fit the density, either crystallography or EM. And this is only the protein part. I guess you're more interested in the ligand part. I'll show you some ligand part as well, how you look at examining the, well, we have 5 minutes?
Yeah.
Okay, so let me show you one ligand part. So the reason I got into this is because I happened to see this notice. So this paper was retracted from Nature some time ago, and this paper regarding a non-heme iron enzyme. bound to a substrate, very complex substrate. So I was wondering why the paper got retracted. So I want to see the electron density. So, and then the PDB entry code for that structure is 4GON based on the paper. I typed something wrong. Okay, there we go. So the structure is this enzyme bound to this compound. I don't know how to pronounce it, but anyway, this compound. It says it was basically removed, no longer available because the paper was retracted. Okay, so now I can't see it. Well, almost not. Remember I mentioned PDB redo? Okay, so go there, say 4GON, and it's there. So everything is there. It automatically refined the structure. Doesn't really matter. The main thing is now it has the PDB file and the MDG file. So I can look at the density and see what it looks like. Okay? So let me just briefly show you what that looks like. So auto MDZ. Okay. So now the only thing we're interested in is the ligand, the substrate. And substrate is a small organic compound. In Coot, there's a little button right here, organic compound. You click on that button, it goes to the organic compound. So click on that. And this is what I saw. This is what you're seeing now. So what do you think based on your expert eye? Let me change the color. Sorry, the color is not clear. What do you think? Do you think there's good electron density for the ligand? I mean, this part of the ring is complete out of the density. So the question now is, how did they build this model? Personally, I would not build a model like this. I would not build a model at all. Not build a model like this. I would not build a model at all. So how did they build a model like that? I don't know. But this essentially is the gist of the paper, how the substrate binds, how the iron contribute to catalysis. So this binding model is critical for understanding the biochemistry of this enzyme. But then the electron density, at least based on this view, based on what was available at PDB redo, essentially is not there. So don't know how that happened. So what I tell my students is, if your life depends on the structure, go look at the density yourself carefully, because that's the starting point for what you want to do. So you really have to spend time looking at this, and Coot is probably the best way. You can also look at electron density in PyMOL, but not as convenient. Coot is actually the best, easiest way of doing that. So that's what I'm trying to show you. I know it's a steep learning curve. I'm sorry about that, but hopefully a few times you'll become more familiar with it. That's the only way, I guess, you can learn how to become familiar with it, essentially. Okay. I mean, this is probably an extreme case. I don't want to scare you. So, all right. So homework assignment, do a little bit of cooting tonight. And then we'll try again next time. Yeah, so I think we're good now. Okay. Yeah.
Yes. So if you have any quick queries, we can have one too. And otherwise you have another 4 days available for discussion. Tomorrow also. Because you go through the literature, see how the structures are defined, what are the formulation combinations, what are the precautions, read the text, and then, because if you think that in 1 week you can learn, it is impossible, but at least you know the basics so that you can start trying on it.
Yeah.
Then we can definitely ask so many things.
But
So,
are you better at PyMOL? Are you more familiar with PyMOL?
PyMOL, how many of you have heard earlier? PyMOL.
More, but still not many. Okay, so we need to do a little bit of PyMOL introduction as well. Okay, that's fine.
Sir, I have a question. Sir, when we are doing the auto-fitting of the molecules in the specific git map, doesn't it affecting the Ramachandran plot, like the phi and psi angle?
When you fit the model,
Yes.
the auto-fitting?
Yes.
Yes, so it does worry about that actually. So the question is, for the auto-fitting program, does it care about Ramachandran plot? I think it does. So it tries to fit in secondary structure element, alpha helices, beta strands. Those typically have good secondary structure. And the loops it builds in generally, the model you saw have 0 outliers. So it actually does a pretty good job. So it's built and also refined. So it's automatically build the model and also automatically refined against the data with all the waters in there as well. So it has been refined somewhat already to fit the density better. Yeah, but still, you can't have mistakes as you saw today. But I should qualify that auto building was done 10 years ago. So if you use a new auto building program, you probably will not see the same mistake anymore. But still, there will be other smaller mistakes probably. So these things cannot be corrected automatically by the refinement program. So manual building has to be done. That's where we come in, to manually adjust the model so that it fit the density better.